I follow you.
Hello. Oh, okay, okay.
So, ladies and gentlemen, as you can see, it will be an IEEE conference. We are very proud that maybe that will be the first IEEE conference in the Faculty of Engineering. And of course we had some IEEE conference in the Faculty of Informatics, but it is a joint organization. So before we start, I would like to mention that, so I'm really very happy that can say this room is really full. So it is very good to see this audience. And we started this conference with Professor Baranyi, but unfortunately he is in China, or he will go to China. And before to start the opening ceremony, I would like to mention that we had a very strong and a very good organization team. And they were really made a very successful work, and we have a very important result. So I would like to mention Nori, Amira, Christina, and Carolina. I cannot see her. And I would like to mention also Anna. I haven't met her for a year, and I didn't know that she had a big change. So some days ago, she sent me a letter that, Peter, please take over all of my duty because I have to go to the hospital. And I surprised, why? And next day we received the very good news that she gave a birth to a baby. So I would like to wish her all the best and to her newborn baby. So I can say that the organization committee was really productive. Okay, so next we can start the opening ceremony, and I would like to invite our rector to give some initial words. The podium is yours.
Thank you very much. First of all, I'm very glad to be here. And I'm even more glad that you are here, with special regards to Prof. Yurii Nesterov. Я думаю, что мы будем разговаривать о очень интересных и важных вопросах сегодня. I also spent 2 years in Leuven in the electrophysiology laboratories of Prof. Edward Carberry. It was an excellent time there. Today, the very important topic is artificial intelligence, with different approaches, physiological approaches, philosophic approaches, scientific approaches, technological and practical approaches to this emerging science and technology. A few weeks ago, Prof. Shaoli were here from the Tsinghua University, who is an expert of the application of artificial intelligence in medical sciences. And I think the forthcoming 2-year symposium, several topics will be recognized in depth because it's a technology of future, a science of future. And our university, as a university with possibly the widest spectrum of sciences, is thought to be able to utilize this technology in depth in different scientific branches. As you can see, regarding the international embedding of the university, we have very strong connections in the USA, in Europe, and in Asia. Probably you can cast a glance at the picture that imposes that our university is a co-chair university of the largest economic development network, the Silk Road network at the university side, which is possibly a prerequisite for the future to drop in artificial intelligence-related sciences in depth. I think a very important date is coming, the last week of April next year, when the Silk Road University Network Presidency Week will be held in Debrecen here. Imagine that the largest economic and scientific development program currently in the world with a presidency week at our university. Therefore, I think that we have several tasks in getting knowledge, in organizing symposia and organizing several unusual things, at least unusual for the universities, namely the use of artificial intelligence in economic development, planning, industrial networks and cooperation networks among universities, financial institutions, companies and regional governments. I wish you a very pleasant forthcoming 2 days, ability to get knowledge and to discuss with giants of this field. Believe me that building personal connections and changing personal thoughts has never been to be less important than everything in the world. And this 2-day period is an opportunity. Please utilize it, enjoy it. Thank you.
So, thank you, Professor Sigulasi, for these kind words. And at this moment, we can open officially this conference, and I would like to invite the general co-chair, Professor András Hajdu, to officially open the conference.
Thank you very much. Ladies and gentlemen, dear rector, colleagues, students, and guests, it is my great pleasure and honor as General Chair to welcome you to the first IEEE conference on crisp and soft computing in AI, modeling and control, jointly organized by the Faculty of Engineering and Faculty of Informatics at the University of Debrecen. First, I wish to express my sincere gratitude to everyone who made this event possible, the organizing committee, administrative staff, especially Nora Todt from the Faculty of Engineering, our volunteers, and all colleagues for their dedication. A special thank you goes to our invited speakers for enriching the program with their understanding contributions. This 2-day conference begins with a plenary lecture by Professor Yurii Nesterov, one of the world's leading researchers in optimization theory, followed by Professor Xuehai Gao's talk on intelligent design systems for large mechanical components. Later sessions will explore AI evolution and digital transformation, applications in mechanical design and manufacturing, data-driven modeling and control, and vehicle and mechatronic systems. Why is this event significant for our university and engineering community? Because AI, optimization, and modeling now stand at the heart of industrial innovation and intelligent system design. Hosting this international conference in Debrecen shows that our university is not only a place of learning, but an active contributor to global scientific dialogue, strengthening our international visibility and fostering collaboration. We also hope that this will be the first in a series of recurring events, building a lasting tradition and a stronger scientific community. Finally, this conference is not about presentations, it is about exchange, dialogue, and cooperation, and about shaping together the technological future we are building. I wish you an inspiring and productive conference, full of new ideas and connections. It is my honor to officially open the event. Thank you and enjoy your stay.
Thank you, Professor Hajdu. And so we can say the conference officially has opened. So we can start the scientific world, and the first presentation will be by Yurii Nesterov. And we can say very proudly that he has a close relation, a certain relationship to our university. When he started to work in Hungary, before that he needed a validation or accreditation his scientific degree, and it was done by our university. So I think all mathematicians in this room knows him, but those who maybe will meet him first, I can say he's a really well-known mathematician. As it was mentioned, he originated from Moscow. He moved to Switzerland, and then he lives in Louvain. Louvain. It is a well-known Catholic university in Europe, but as you can see, maybe it is written a little bit with mistakes, so he also has a certain position in the Corvinus University. And so I can continue, and I have maybe 3 pages about his achievement, but I would like to emphasize only one thing. So he received a lot of prizes, awards, and maybe the most prestigious is the Neumann Theoretical Prize, which is given maybe so this is the highest prize in the field of optimization and operation theory, and of course he deal with, and we can say he is one of the pope of convex optimization. We can learn a lot of things from him, but I hope that you can consider that here the main part of the audience is not mathematician. And so, Professor Nesterov, the podium is yours. We are waiting for your presentation.
Can you switch? Okay. Okay, this is better. Okay, thank you very much for this nice introduction, and it is always a pleasure for me to be here and to speak in this beautiful auditorium. So my talk today is not very usual. So usually I'm speaking about optimization methods and optimization theory, but now the time is really very interesting, and today I would like to speak about the challenges which we have in optimization because of the development of artificial intelligence. Okay, so in the audience, I see many young people which maybe don't understand that, but people of my age understand very clearly that we were living during decades in the age of revolutions. The first revolution was the revolution of personal computers. After that, there was the revolution of internet and telecommunications. After that, we had the algorithmic revolution, which is necessary to understand how we can use all development of the previous 2 events. And the last revolution was very recent. This is the big data revolution. Very big challenges in all these times, and now we understand what it was about actually, because after that we can see maybe the main event in the history of science, at least in the last 2000 years. So we can see the birth of artificial intelligence. Without this previous revolution, actually the birth of artificial intelligence was just impossible. Now, so it happened around 2012 when people started to speak about deep learning, neural networks, and so on. And now the artificial intelligence is, of course, alive. And its main goal, of course, is to support the human intelligence. But also, so artificial intelligence, now it is more or less clear, so it can produce the decisions which compete with the decision produced with human intelligence, and artificial intelligence is very young. So actually, our goal now is to help its development in the right direction. And in order to understand how this can be done, so it is better to look at our experience in the supporting of human intelligence. In order to support human intelligence, so we have the structure of many sciences, and let me show you the, let me say, some classification. Of course, it is very, I don't know, aggregated, but still, so we can maybe see what's going on. So in the structure of sciences, we have one very special science, which is mathematics. And about mathematics, we will be speaking a little bit later. But after that, we have the big group of exact sciences. What are exact sciences? Exact sciences can predict the future. The models or the laws in these exact sciences are so good that we have with high probability, high accuracy, predict what happens with our system or whatever. So in the future. So these exact sciences, we can see the physics, chemistry, and all things like that. After that, there is a group of inexact sciences. What can do inexact sciences? So they can explain the past. If something happens, so they can understand and explain very well why. And in this group, so we have economics, history. No, this classification is not indeed very exact because there are sciences which are in transition from inexact sciences to exact sciences. For example, medicine, it is somewhere in between. Medicine is not only the post-mortem analysis, but it is also, so it can predict in many situations what can happen. Yes, and also there is one more science. So this is philosophy. Philosophy, so can explain the internal nature of things and processes. Okay, and this is about everything, actually, the nature, life, and society. Now, philosophy maybe is not so important as before, but know that in the beginning of the development of sciences in ancient Greece, so this was one of the main, only science which existed, and up to now we pay some respect to the philosophy, because our degree, doctoral degree, actually PhD, this is the doctor of philosophy. This means that we are supposed to be able, so people which have this degree, to explain something, what happens in general in the world. Now, the justification, the way of justification which we have in all this system of sciences is mainly verbal. So this is more or less convincing reasoning. So except maybe mathematics, but also in mathematics we also have some convincing reasoning. And so all results of artificial intelligence, actually they are supported by computation. So this is the completely different way of justifying the results, which means, so artificial intelligence need a creation of system of new sciences. Sciences which are very different from everything what we have for human sciences now. Okay, and this process has already started, actually. We can see in which direction we should modify our usual sciences in order to use them for artificial intelligence. This has already from transition from mathematics to computational mathematics. So this started actually a long time ago. Actually, the terminology of artificial intelligence was introduced in 1956. And this is more or less the time people started to develop very intensively computational mathematics. So what is the difference between mathematics and computational mathematics? Let us look. So what is mathematics? Sorry, I repeat the evident things, but we needed to compare with other things. Okay, mathematics. The objects are abstract notions and axioms and theorems. Methods are logical proofs. And the results are perfectly correct statements. So in forms of theorems. And the goal, so actually of pure mathematics, is generalization. So we want to explain as many events as possible by some powerful theory, generalization. Yeah. Now, so in mathematics, maybe this is the only science which has a monopoly for the absolute truth. And in some sense, mathematics can be characterized as an art of discovering immortal facts about immortal objects. Now, what are behavioral rules? How the pure mathematician works? First, there is absolutely democracy in terms of the questions. Whatever the questions which come to the mind of pure mathematician, it has a right to be answered. And mathematician is allowed to think in this direction as much time as he wants. Now, the older the question is, the more prestigious is to find the answer. Everybody remember the story with Fermat theorem, Poincare conjectures. So in some sense, so this is a kind of progressive jackpot principle. The more people tried to solve the problem and failed, the more prestigious is to find the answer. Yeah? As a result, so many important problems remained unsolved. So if you open a book on combinatorial optimization, so it is full of hypotheses which we have for 100 years, and up to now there is no chances to find the answer. And it is important that the mathematics is the only science where time, the usual time of the usual human life, plays no role at all. It doesn't exist in mathematics. In all other fields it exists. Take anything and you find the importance of time. In mathematics, not. Now, computational mathematics. For computational mathematics, the objects are mathematical models, methods are numerical schemes implemented by computers, and results. What about the results, important results in computational mathematics? At the beginning of computational mathematics, people thought that this is numbers, the result of computational experiments. But now it is clear that it doesn't work. Doesn't work. So if you look at the computational results which were produced 50 years ago, they are not interested at all. The models were different, the computers were different, the speed, memory, everything. So computational results become absolute very quickly. Yeah, and therefore the accumulation of knowledge in computational mathematics also is possible only in terms of theorems. Things which we proved about numerical methods 50 years ago, they are still valid and still important. Numbers, not. So computational mathematics, therefore, it is not the experimental science, it is a mathematical science. Now, and the most important questions now in computational mathematics are related to computational time. How much time it takes to solve problems. Now, the goal, you remember that in mathematics, this was generalization. In computational mathematics, it is opposite. It is specification. We want to find the best method for this particular problem. We don't care about methods which can do something with all problems in the world, and normally it is not very interesting at all because it is very weak. So, but for our particular problem, we want to find one best method. Now, behavioral rules. So the open questions, the importance is measured by practical consequences. So the old problems, they quickly lose their relevance. Yes, and therefore all really important problems are solvable in the sense that if we cannot do something 1 year, 2 years, 3 years, we forget about that. And we do something different in the same style, and life goes on anyway, so it is important to move forward in computational mathematics. And this is, therefore, this is another mathematics, but it is suitable for the needs of artificial intelligence. Yeah? Now, if we accept all of that, so we can think what can happen with other fields. We can imagine that we could see the computational physics, computational economics, computational history, linguistics, and so on, so with much better predictive power. All of that is quite possible, and this is more or less the goal which we have now in the different domains, the creation, this new domain. But what about computational philosophy? What about computational philosophy? So for me, it is very difficult to imagine what it could be. But I recall you that philosophy is necessary to explain the internal nature of the processes and the things and all things like that. So the new system of sciences needs some replacement for philosophy. And the remaining part of my talk, I will try to convince you that this can be done by optimization. Optimization can replace philosophy in the structure of sciences for artificial intelligence. Why? Let me recall you some things which many people know. So there are optimization principles which work in nature and social life. So the best citation is from Leonhard Euler, the famous mathematician, which tells us that nothing takes place in the world whose meaning is not that of maximum or minimum. Yeah? So optimization is everywhere. For us, it is interesting, so this takes place, because takes place is about the methods. Yeah? So how it takes, how come that it takes place. So there is always algorithm behind, and we know about algorithms, so in nature and life, so we know something starting from ancient Greece, which said that the God's milk green slowly but surely. This is about the methods and the rate of convergence. But the examples are, of course, very many examples. So minimal energy in principles in physics, propagation of light, for example, this is Fermat's law. In economics, rational behavior of consumers, many things like that. So as a consequence of the existence of this minimal energy, or this maximum minimum, is the predictable behavior. If we know that some system or process or whatever agent is going to minimize something, we know his destination, yes, his final point. So we can have predictable behavior of the system. And also what is interesting for us as a specialist in optimization, we can discover new optimization scheme from observing some processes in the nature life or the social life. Yeah, so this is, let me, yeah, and then so what we can take from this, so we can use this needs of artificial intelligence. So, and in my talk, I'll try to show you several examples because they are not immediately evident for usual people. Where do we have optimization in our usual life? And let me start from the gradient type methods. Okay, so this is the method for simplest optimization problem. We have some objective with finite number of parameters, and we want to minimize it, so finding the best value of the parameters. So the method for solving these problems, the simplest one, the gradient method. Yes, we can compute the gradient, the vector of partial derivative, and go in the opposite direction, was proposed by Cauchy. Augustin Cauchy in 1847. In 1847, he observed that this problem can be solved by these numerical methods. Cauchy was a pure mathematician, of course, and it is interesting that after this discovery, during more than 100 years, mathematicians didn't have any necessity to develop a new optimization scheme or better optimization scheme. For pure mathematicians, so the problem was solved. So we have the problem, we have the methods, what do we need else? The next method, which is better than gradient descent method, so was proposed 100 years later by Boris Polyak, and it was the heavy ball method. So let us look at the difference. Okay, so in the gradient method, so we modify our position looking at the gradient at the point, so it is like a descent to some surface. But if we want to move faster, we need to take into account the inertia. Yes, we need to take into account inertia, and then so our trajectory will go in a faster way. So this was a kind of intuition. It is important that we collect information about curvature of our surface at the point where we are now. Okay, something just to avoid the situations like that. Yeah, it was 1964, the first new method so in optimization, and you see it is already the time where the notion of artificial intelligence was alive, and people started to develop computational mathematics and so on. Now, next question, can we move faster than that? Can we think about the process which moves faster than that? And the answer is yes, of course. Yes, of course. Let us just modify a little bit this formula. How? So this was done in 1984. So what is the change here is the point where we collect the information about our curvature of our surface. It is not at the point where we are now, but it is in the predicted point. We look ahead, and there we collect the information about the curvature. Now, can we say what is the process in real life where we act exactly in this way? Of course, everybody who is driving cars knows that it is too late to look at the road just at the point where you are. You should look ahead and adjust your wheel accordingly. Then you can move faster. And this is exactly what happens. So you see that all main processes with movement, walk, run, and drive, so have some features of optimization methods inside. And our job as mathematicians is to transform these intuitions into some theories. For example, for this, it is called fast gradient method. So what we can say how quickly the residual between current value of the objective function and the optimal value decreases as a function of iteration, number of updates of our states. It appears that it is 1 over k square. After that, we can prove that we cannot do better and all things like that. Yeah? So all theories, but about the processes which already exist in the real life. So therefore, we can say that the main goal of theory which we have in computational mathematics is to provide all methods, and in our case, all optimization methods, with performance guarantees in terms of computational time. So you see here again the most important notion, computational time. Okay, and this defines the field of applications of our schemes, because it is a very big difference if our problems can solve in 1 millisecond, second, hour, week, year, and so on. So it defines where we can apply the corresponding scheme. So let us look very quickly just what we had in optimization, the progress in the performance of optimization scheme. So I will show you just how it was in terms of the number of iterations, number of updates, and we take just a sample value for the number of iterations, 100. See what's going on in 66 for subgradient method. So we prove the rate of convergence 1 over square root of k. Square root of k is 10, so which means that we had 1 right digit after 1 iteration. In 72, 1 over k for the gradient method, 2 digits. In 84, 1 over k square, 4 digits. In 2008 cube, 6-digit, 19 for 8-digit, and 22 10-digit. So you see, so the performance of the method becomes higher, higher, and higher. Of course, for that, so we need to use the derivative of different orders, so which may be difficult to compute, but actually very often the data of our problem is sparse, and therefore all these methods can be implemented more or less in similar computational computational time. Okay, so this is what happened in optimization theory. But why do we say that optimization principles are really, optimization methods are everywhere in the life? So in order to see that, I'll show you an example from economics. From economics, I think many people had, in one way or another, looked at this theory of rational consumers, where the agent must maximize its utility function. So this is an assumption. This is an assumption, and but the question is, at least for people which are doing optimization, it is a very important question: how we can rely on rationality of consumers if the normal people simply have difficulties with normal arithmetics? You know, in optimization methods inside, there are quite serious computations. We need to invert matrices or compute determinants or whatever. How comes that normal people apply such difficult things? Yeah, and this is an important question because, you know, we are trying to develop mathematical theories. Yeah, so as we have seen, mathematics is important for computational mathematics. And in mathematics, unjustified assumptions are very dangerous. People understood that just in the beginning of development of economics, actually, one of the classical guy in economic theory, Peron, which is Peron-Frobenius theorem, just suggested the paradox where he proves in a rigorous way that maximal integer is equal to 1. The proof is so simple that I show it to you. It takes one line. So denote by n the maximal integer. Okay, since 1 is an integer, n is greater than 1. Now, n is positive, therefore we can multiply the two parts of this inequality by n, then we have valid inequality, then n is smaller than n squared. But n is maximal integer, therefore n squared is smaller than n. And you see, so the only solution, non-zero solution of this inequality is 1. We proved that the maximal integer is equal to 1. Yeah? What is wrong? Actually, people in the audience may think so. What is wrong? And what is the difference from the standard beginning of economical paper when we start denote by x star the market equilibrium? Okay, so what is the difference actually? Market equilibrium. Then, so we can prove something. Yeah? Before we can proceed, we need to prove that this guy exists, does exist. Yeah? If it doesn't exist, so we come to the stupid conclusions. But in economics, it is even more complicated because we need not only the existence, but we need that this equilibrium is achievable by the agents. Yeah? We need to prove that the agents are able to come to this equilibrium point. How? So this is again the question about numerical scheme. But fortunately for economists, so there is indeed the answer from the optimization theory which can explain how people optimize in real life. And I show you again, so this method. So I call it intuitive optimization, but actually in optimization theory this is called random search. Let us look what is it. So it has two parameters. One, very small parameters mu, really very small. Infinitely small. And relatively big parameters. This is a usual number, 1, 2, 3, I don't know, any big numbers. Now, we're staying at the position x. And at this position, we get a possibility to change, to move from this position along a random direction u. And we need to decide, should we go there or not? For that, we compute this estimate. Actually, it can be just the approximate and so on. So we move along this direction a little bit from x and see what happens with us. And compare it with the step size mu. Yeah? So this is the sense of this formula. So it can be approximate, but actually the move can be very small. It can be even virtual experiments or, I don't know, intuition or whatever. What happens if we go there? So we just in mind decide, yeah? And how much it will change your satisfaction and so on. So after estimating this delta, which is really not a big deal, yes, so we do an important decision. We change and we go with big step h along this direction. Yeah? Now, what happens? So if delta is positive, we see that our expenses are increasing. We make a big step, but in the opposite direction. We don't go there, we go back. If it is negative, which means that this direction is good, minus by minus is plus, we jump along this direction with again with a big step. Yeah? So this interpretation doesn't look very clever. Yes, with common wisdom, is this just a kind of panic behavior because very small experience, new experience, result in very big change in your situation. But actually it is not. It appears that this is exactly optimization scheme, but for another objective function, not for our f, which is somehow the expenses, but the expectation of disturbance which we have from random expectation of the losses which we have from random disturbances. So, which means that in this way, so we minimize this objective function, not that, but this. But from the theoretical point of view, this is the same, because still, so the agents which are implementing this scheme, they become predictable. We know where they go. They go to the minimum of this function. But of course, it is different from this objective function f. Okay, so we can prove, know everything about this process, so rate of convergence and so on, but it is important that the process is so simple that this behavioral pattern is accessible even for animals. Animals, they do more or less such things. They try something, if they don't like, they go in the opposite direction. If they like, they go in this direction, and that's it. This is explain rationality of animals in many situations. Okay, so now I have some time, and I give you one more example from optimization methods from the our life, efficient optimization methods, and it is related to one procedure which actually is very important in data mining, data analysis. It is used everywhere, in medicine, in I don't know, economics, and so on, biology. So it is clustering. Yeah, clustering. What is clustering actually? So this is the aggregation of the data. We have data pattern, many data patterns, VI, and we want to classify them, which means that we want to attach them to some centers with a small number of centers. Yeah, so we want to represent the big population. So we are using some centers, so to attach it to the clusters. So this is indeed the problem which people started to think about that from the very beginning of computational mathematics in 50s actually, how to solve that. Okay, so how to represent the big arrays of data by small representatives, for small number of representatives. So the main assumptions, at least if we speak about soft clustering, is that we have membership value, which means that each element of our data participate in cluster K with certain degree or certain probability, Pi. Okay. Now, what is this PIK? Okay, I am sorry, but this is a purely engineering approach. When they don't know how to define PI, they just take the expression which looks reasonable, it works in the right direction, and yeah, so this is PI, is more or less like that. So the closer if this guy to the center, the better is, okay, so this probability, yeah, something like that. And again, so engineers like to have many parameters. So here there is this sigma, parameter sigma, which is called falsifier of the system. Again, don't ask me why it is falsifier, but usually when people don't know how to take this parameter, they choose, the usual choice is sigma equal to 2. Anyway, so there is some formula which gives us the dependence of probability on the position of the centers, because VI are fixed and centers are flexible, so we need to choose their position. And after that, so mean clustering, again, if you open books on clustering now, so it is one of the first model which is considered there. So we minimize this objective function in the position of the center. From optimization point of view, this is a terrible problem. It has many local minimums, and it is difficult and very difficult to find global minimum, and different methods give you different solutions, but still for practitioners, they get some solution from the computer, and this is enough for them. Yeah? So up to now, so this problem in the strict sense remained unsolved. Now, and the main question was, can we have the data representation model? So, can we have a data representation model which have only one solution and which the solution is easy to find? And there is always a hint if you want to find something efficient. So you need to look if such things, they do exist in our real life. Because the processes which we see in our real life, they are already checked by many years of experience, and since we keep them, they are good and efficient. Yeah, this is the common wisdom. And in our situation, it is more or less almost evident what we can have as example of clustering in our real life, especially after the presidential election in the United States. This is sequential electoral procedure in democratic context. Because if you look what we do during the election, so this is exactly the clustering. People vote, and therefore the whole society is divided by some clusters, clusters which support the different candidates. So can we indeed take this example in order to create an efficient clustering algorithm? Okay? Let us look at that. So I have, how much time do I have? It seems I started later, so maybe, I don't know, 10 minutes. That's it. Yeah? Okay, so let us look at the voting model. So we just developed it in a couple of slides. So we have n independent voters, and we have L political parties. And we need to cluster these guys, attach them to the parties. And the main assumption is that the result of personal votes are random. This means that each guy with some probability, maybe almost zero probability, by mistake, whatever, votes for any political party. Now, therefore, let us introduce this probability. It is just notation at this point. And this is exactly what we want to know, with which probability the guy, I, votes for different parties. Yeah, this is the output of the model. Now, so what is the data? The data is personal opinions. This is the vector of VI, so initial data which we want to classify. This is their personal opinions. And this is fixed. Yeah, this is our data. And also, there are also the flexible position of the parties. So because they want to attract as many voters as possible, so they can change their position to become closer to the average opinion of the voter. So this is also unknown, will be result. Now, so we need to define the probability. You remember, so at the previous slide, there was a probability with, I don't know, ratios of powers, of distances, and so on. We will choose something simpler, which corresponds more or less to the economical theory. It is called the logit model. The probability that the guy K votes to the party I is proportional to the distance between xk and vi. So we need to choose the metric, and we measure distances, and then we have this probability. So in economical theory, it is called the logit model. Here we have the parameter mu, okay, the volatility parameter, flexibility parameter mu. When mu goes to 0, then we vote always for the closest party, for sure. If mu is positive, then there is non-zero probability to take the other guy. Yeah, so it is explaining the flexibility of the guys. Fine. Now, this I already said. Now, what are the party doing? Party should react somehow at the opinion of the voters, and we assume again that for each party there is a kind of constitution, something which they do not change, they never change, so that what they're going to do. But in order to adjust the public opinion, they minimize these objective functions. What is this objective function? There is a distance between constitution and the current position. Yes, and after that, so we take the average distance to the guys which are going to vote for us. Yeah, so as a function of the position of xk, position of the party. Vi are the position of the voters. Yeah, so if we minimize that, so we get the current best position of the party, which depends on the probabilities. Yes. Probabilities of the voting is here. We look at the results of the previous elections. So from them we know this probability, and now we adjust the position of the party. So this is more or less exactly what happens. Here you have some tolerance parameters. You see here the penalty parameters, so which gamma goes to 0, this guy goes to infinity, and the party always will be at its constitution position. If it is greater than 0, then so we can diverge. Something like that. Yeah? Simple model. Okay, so there is interpretation of this guy as the expected distance to the attracted voters. Okay, so since this function is convex in xk, the solution is always unique and easy to see that, but actually the model is done already. Yeah, so what we are doing, we can only see what happens in the voting process, where given the position of the parties, we compute probabilities, which means that we vote, and after that, when we vote, okay, we update the position of the party. So exactly this alternating behavior. This is it. So the model is done. So the only what we can do is to try to understand what happens with these guys. Okay, and in our process, we know what we want to have. We want to have a stable process, which means that we want to prove that this process has unique convergence point and see how quickly we go to this point. And we have only two parameters. Mu is the volatility of the voters, yeah, in the logit model, and gamma is the flexibility of the parties. Yeah, so, and then, so if you look at that, it appears that everything is fine. There is natural condition that gamma is smaller than 1. Then the corresponding electoral system is stable, which means that the unique point of convergence, and we know even the rate of convergence, how quickly we go to this point. It is linear rate when gamma is small to 1, so this right-hand side goes very quickly to 0, so the process is convergence. And okay, the auxiliary problem the party need to solve is the minimization of this guy. And we even know the interpretation of this condition. Gamma is smaller than 1, yeah? So gamma is here. Mu is the volatility of the waters. So which means that the level of conservatives of the party should be smaller than the volatility of the waters. So which means that the system is stable if we avoid excessive populism. So parties shouldn't go too far towards the public opinion. We should keep some distance to their initial, let me say, constitution. We know this from practice, actually, from history and so on, but now, so the good thing that this is a theory. So know that it's definitely true. So this is the second example, but the question is why I'm speaking that this is optimization. Because it looks like as an alternative process, but it appears there is optimization inside. And all these guys, the parties and the waters, they minimize this objective function. This is the joint potential function, and therefore, from the viewpoint of the game theory, so this election, it is not antagonist game. So both end parties and the voters, they have joint potential, joint goal, which they want to minimize. And this is the reason of stability. Okay, and our process is a kind of alternating minimization scheme for this objective function. So if we have position of the parties and minimize this in probabilities, we get the probability distribution, and we fix the distribution, and minimize in X, we update the position of the party. So, and this objective function is convex, which means that unique solution and good behavior of the optimization methods. For people which work in convex analysis, I would just try to prove that, because actually here in this structure we have very non-trivial term from the viewpoint of convexity in the middle, which normally shouldn't give the convexity of the system, but here, so everything works properly. Okay. Now, and again, from the viewpoint of optimization theory, so alternating minimization is a natural technique in optimization theory, but there is almost no example where we can prove that this alternating minimization works well. And here it appears it works very well. We have linear rate of convergence to the solution. Okay, now, this is more or less all what I wanted to say today. I think you have seen that optimization theory is necessary for understanding many processes in nature, life, and society. We have many, many more examples, but I have no time to speak about all of that. And optimization also can provide the artificial intelligence with models and methods which significantly increase its predictive power. Remember that for good predictivity, we need not only the models, we need good models, models which can be efficiently solved by optimization scheme. Therefore, optimization is very important for many domains, so we are only in the beginning in the process, and I hope that sometime we will have the degree Doctor Optimization, which should replace old-fashioned Doctor of Philosophy. Okay, thank you for your attention.
So, thank you for this really very interesting presentation. I would like to add some remarks, and later you will have time for questions. So it was really excellent, but please go back to your third slide.
Third slide? No, that's difficult. Wait a moment. Third, number 3?
Yeah.
Wait a second. No, it should be.
So may I ask my students, could you follow all the presentation?
There is no home button here at the computer.
Yeah.
Control home. Ah, okay, yes.
I think it was excellent. Yeah.
Stop.
Yeah.
The whole.
Yeah, it's okay. Yeah, it's okay. So, you mentioned the exact science can predict the future, but I missing the engineering science, which create the future. Yeah, and
I'm sorry, you know. Of course.
yeah, and also I would like to. So you mentioned we can predict the future. You show us a prediction. What will happen in the engineering science? So believe me, in the engineering science, we will use this mathematics which was presented here. But, so I ask again, my students, could you understand everything from the mathematical point of view? Please be honest. Maybe not everything. So I followed that. Okay, my students can understand this, that, and at certain part of the presentation, I recognize, oh, my students may not understand the mathematics. So what I would like to mention that we will include more and more mathematics, but we have to teach the mathematics for the engineers in a little bit different way. So it is a very mathematician approach, and it is excellent, and I really enjoyed it, but we need a certain translation.
Yeah, but you know, for example, for clustering, so the first soft clustering, this model of clustering, which I don't like, was created by engineers, not by mathematicians.
Yeah, but you know, I lived with my colleague in Japan, and you know, in Japan they like manga, and we say we have to make our presentation close to manga. I mean, more figures and more explanation. Anyway, thank you. It was excellent, and we have a certain time for questions. So that is important. You can meet a really well-known, highly ranking professor. So please use the chance to ask questions. So maybe questions from the mathematicians, or okay.
I have a question that we know there's no free-lunch theorem for machine learning, no free-lunch theorem, there is no best algorithm in general. The question is the same for me now for optimizers. So we can say it's faster, a bit better, and so on and so on and so on, but I would guess that I can show a counterexample when it will not work that nicely. So what about this no free-lunch theorem for optimizers? No free lunch, meaning that I cannot say that there is a best algorithm for everything. It's proved.
First, I would say that I wouldn't agree with this non-free lunch theory. Sometimes, sometimes there is free lunch. If you look, for example, what happens with the fast gradient method. So instead of the gradient method, we have fast gradient method at computational cost is exactly the same of iteration. So it is exactly method of the same style, and we have much better rate of convergence.
Sorry, but does it hold for all the functions?
Yeah, well, at least not for all functions, of course, not for all functions, because gradient method is a very general scheme which works everywhere. And here we need to restrict ourselves to good functions. So yes, of course. This is the same story with interpretation. You remember, interpretation we go by foot, or we run, or we drive. Of course, you drive faster, but you need good road. If the road is bad, so you cannot do anything, yeah? So the same with the method. So you have free lunch, but for the roads. And there are many situations like that. Usually, you change a little bit the So mainly, so for the increasing the efficiency, you pay by the reduction of generality. Okay, you prove that your method is much better, but the smaller class of problems. But again, so very often it is a free lunch because you are, if you are engineers, you are interested to solve this particular problem. And as far as this problem remains in this reduced class, that's fine for you. It is free lunch. But of course, if it doesn't, so it is another story. It's, yeah.
Okay, thank you very much.
Depends. Thank you.
So, I ask my students, who dared to take a question? Okay, so, okay.
He's not your student, I guess.
Yes. But if you were so kind that you already were watching me and whether I have a question as a mathematician, of course, I understood the mathematical part perfectly as well, and thank you very much for this very nice presentation, Yurii. I would have a question or rather a remark still to this first part, so to say. When you made also a classification, mathematics, and you called the so-called computational mathematics. Yeah. And in computational, you focused on mentioned numerical methods. I just wanted to mention that is an important part that so-called computer algebraic exact methods there, which might, or which not might, but which have also strong connection to AI as well. So I hope you agree.
Yes, of course. Yeah. I don't say that this is okay, just, yes, especially now, because you know, now when you go to the conferences, very often at the same conference in the same sections, actually, you meet pure mathematician and applied mathematician, and they have different, let me say, understanding of the priorities and so on. But it is just because so we're at a bifurcation point. So we just started the development of new philosophy in this science, but in the future, I think it will be more and more transparent. So it's, yeah.
Thank you very much. Thank you.
So, any other question? If not, thank you again for this very nice presentation.
Thank you very much.
And so we have to, yeah. So we had a presentation for a young professor, but you are young for a long time. And now, to balance, we really need the younger generation. We have to balance it. And so the next presenter, a little bit younger, and he will, yeah, please, he will present something, it is more engineering presentation dealing with 3D modeling, finite element calculation, and this technology. So intelligent designing system for huge bearing systems of maybe for turbines system, but so Professor Xu Gao, please start your presentation. Do you need any technical help?
But I think I have connected this line, right?
Yeah.
No response.
So,
okay.
I ask the technical background. Technikai segítséget szeretnénk. Yeah.
Excuse me. Yeah, because I use WPS.
Computer?
Yeah, yes.
I think it's your computer need to share, you see?
Yeah.
This one.
Oh, okay. Thank you.
Okay.
Okay, I will use this microphone. Good morning, dear colleagues. I'm Gao Xuehai from Shanghai Dianji University. It is appreciated to have the opportunity to report my team's achievement in intelligent technology application. The topic is intelligent design system for huge bearings. My team mainly focuses on the intelligent technology application in engineering practice. So today I bring you a specific case. This is the contents. Sorry, I don't know why. The slides will skip automatically.
Because you touch this one.
Okay.
And in here.
Okay.
Yes. And
Okay, do not touch this.
yes.
Okay, sorry. Thank you. I will use this. In bearing industry, taking the wind turbine industry as an example, that's my research interest in wind turbine industry. Yeah, we can find that, especially in China, recently the new huge bearings produced one after another. The development is very fast. So that gives us very, very short development lead time, then insufficient test and validation. That leads a lot of unexpected failures in field. Then the question arises, how to shorten the development lead time and while keep or increase the product reliability. Then I think the intelligent technology may give us a kind of solution. This is the outline of our intelligent system. For presentation convenience, I divided it into intelligent design aspects and intelligent manufacturing aspects. In intelligent design manufacturing, that includes the automatic failure model analysis and parameters scoping and parameters driving modeling and drawing, a fast finite element analysis, and fast PPAP. In intelligent manufacturing aspects, that include the dynamic manufacturing resource assessment, dynamic process schedule, and process real-time monitor, real-time data record, and dynamic quality management and assessment. Today, I will only focus on the intelligent design aspect. When we design a product, usually we start with the failure identifications or the risk identifications. Although we have done a lot of works, but there's still a lot of unexpected failures, or even some failures, although we expect it in advance, but they still happen in engineering practice. Why does this happen? We think there are three key factors. The first, we design according to the design guidelines, standards, design rules, but these failures are not covered in guidelines. Then the second, the product designed by our engineers, but our engineers have their own quantification limitations. They just know what they already learned, but they don't know what they haven't known. The third is that although we recognize the risk, but we follow the design rules, but the scenario we use, it is beyond the assumption of the theoretical assumption of the design rules. So how to solve these three aspects? For the risk, we haven't recognized, or the risk unexpected. Yeah, as I said, the design guidelines, the engineers know what they have learned, but they don't know what they haven't known. But all the similar risks, they already exist in historical data or some similar application scenarios. Then how to fully take use of all these data, all these informations from the historical or similar applications? Yeah, we developed the intelligent FEMA system as this. The workflow and the key technology involved. In the first step, we acquire the failure informations from all the internet resources, like academic references, like the standards online, forums, and sometimes short videos that give us a lot of failure cases, a lot of information. Here, the key technology we use is the web crawler. And then we get all these informations, but this information is relative to our design purpose, maybe not so relative to that. So we have to do some data cleaning. Here, the key technology we use the natural language processing technology. Then we get all the information related to our design objectives. We need to process all this information to formatted FEMA words. Then as an engineering application, we just use the current mature AI models. Here we use this DeepSeek embedded into this system. In engineering practice, we found although the AI helped us a lot, but there's still some mistakes or incorrect descriptions, so we still need some personal or some manual processing. At last, we get the FEMA, and then we output the design rules or design checklists for the engineers. Now we are developing the automatic design from these design rules, but currently we still use the human processing. Now this is the architecture of our developed FEMA system. Yeah, in this system, it includes 3 key databases. The first is the expert knowledge database. That's the result, that's the knowledge or the achievements we from our team, our research achievements. And some items are provided by volunteer researchers. That's high quality FEMA items. And then the second is the individual knowledge database. The individual can use the FEMA technology I just mentioned to set their own personal or individual database. They can get access to their own database through the account, registered account. That's free. And at last, if some enterprise want to use this, I think about the information security. So they have we give the enterprise the private database. They can input or they can input their own FEMA database or their own knowledge into this. That only the authorized enterprise guys can get access to the enterprise database. That's the whole architecture of our FEMA system. And we are developing the AI design checking or AI automatic design in technology, but that's ongoing. For the third factors, although we recognize the risk, but the design proved to be failed. Yeah, here, I take the bearing raceway fatigue model as an example. In wind pitch bearing, when we design a bearing, we calculate the bearing life, bearing raceway life, use the model in that block, in that box. But when we design, we calculated the raceway damage, 1, point X, or 2. What does these numbers mean? That means the bearing is okay or not okay? But in application practice, in engineering practice, we found these numbers means nothing. Even we design with a raceway damage below 1 or even 0.1, 0.1, we still found the failures. So here, but the wind industry exists for many years. And here we collected more than 300 cases. And then we learn from these cases, we set our own criteria for the raceway, yes or not, okay or not criteria. Then we use the raceway damage, but this damage threshold is not set at 1 or whatever. And we use the raceway contact pressure distribution as a plus criteria for us to judge the bearing okay or not. That's our work, how to identify risk and how to solve the risk. And then with these calculations and FEMAs, we get the key parameters of bearing, and then we can, with the help of a computer, we can get the 3D model and the 2D drawing of the bearing. That's very easy, I think. So nothing to details. And then when we modeled the bearing, we designed the first draft of the bearing. But in engineering practice, especially for huge bearing, we found that the traditional design rules are usually failed in our design. Why that happen? You can see for common bearings, the design is based on Hertz contact theory. The assumption of that theory is that the deformation occurs only at the rolling ball or roller's contact region, together with the contact region, and neglect the hull ring or hull system deformation. But for huge bearing here, I mean huge, the bearing size is more than maybe 5 meters, even sometimes 8 meters, 10 meters. This bearing deformation is so huge. And the contact region, the raceway rolling elements contact region deformation is nearly negligible to the hull ring deformation. So how to solve this? The finite element analysis usually used in here. When we use FEA technology, now we have to face 3 key challenges. The first is that a huge bearing, usually we have hundreds or thousands of contact pairs in bearing modeling. FEA engineer knows that thousands of contact pairs, it is a disaster for convergence in simulation. And the second challenge is that the mesh size. You know, the contact region, the rolling elements or ball and the raceway contact region is so small, but the whole system, the whole bearing is so large. How to mesh the elements is a challenge. The third is that the boundary condition for the complex bearing systems, how to set the boundary condition. Yeah, we have worked in this field for many, many years, developed or improved a lot of models based on the nonlinear bearing elements. But in today's topic, we will not discuss this in detail. When we give this to the enterprise still found that it's very, very time-consuming and complex for engineers to handle this modeling process. So we developed some fast FEA model with very easy parameter driving C# and ANSYS development. That makes the FEA workers very easy and fast for even some junior engineers to do these FEA works. Another thing is that for bearing, it is the structure. It is very simple. It's a circle, so it is very easy to achieve the feature-based processing planning. We have done this. For totally new products, we use AI technology to identify features in the bearing, in bearing, and then do the process planning with AI technology. Then do some parameters updating accordingly. In enterprise application, most products are similar, very similar to the existing products. So we just identify the similar products to existing processings, and then just extract their existing process, updating the key parameters. Then after all, we output the processing documents, the cost evaluation, and the machine learning codes. So that gives them a whole design process from the start, risk identification to the processing codes, manufacturing codes. That's the whole workflow. Then, sorry, maybe a bit faster. Then we go to the summary. First, the big data-based intelligent design technology that help us to identify risks and extract the key design factors from massive historical experiences and some similar scenarios. Then with this, we can, design a bearing, design a product, think more than individual engineers. And the second, that with the AI network technologies, the entire process of parameters optimization, modeling, manufacturing, now it is integrated in a closed loop. That is very good in efficiency and reliability improvement. The third is that here we use the FEA technology in huge bearing systems with integrated computer technology that will help us to increase the modeling efficiency and solve the convergence with high efficiency. The third is we use the PPAP, computer-aided processing planning here in bearing, because all the data flow is closed, so that is very easy to do this. Or in future, we are doing more works that to embed it more AI technologies in the whole design and manufacturing process to improve the efficiency and to reduce the human works. Currently, we haven't integrated the maintenance in the product life cycle into this system. In future, we will integrate the design, manufacturing, and maintenance in this system to optimize the bearing from the whole life cycle. That's our work we want to do. At last, yeah, I would like to introduce my team. We mainly focus on the drivetrain, the bearings, gears, and so we have some vision technology and vibration technology experts. Our team mainly focuses on the enterprise works, on the technology application in engineering practice. So that's our team. Sorry, maybe a bit faster. Thank you.
Thank you for your presentation, and so I really appreciate your timing. So we are a little bit lagging the program, but we have to ask some questions to him. So please ask a question. I encourage our colleague in the field of mechanical engineering. So, sorry, I am electrical engineer, so I am interested in the finite element methods, but also for electromagnetic fields.
Okay.
So it's a little bit different. So, Peter, a question?
Dear Professor, thank you very much for the questions, for the presentation. It was very interesting. My question would be regarding what would be the vibration caused by the, I would say, the unmodeling uncertainties. Okay, so could you tell me something about how to handle unnecessary vibrations due to rolling based on your method?
Excuse me, I didn't catch it. Uncertainty, what? Uncertainty, excuse me. Can you repeat that a bit slowly? Yeah.
So unmodeled dynamics.
Yeah. You mean the model or the data usually limited? Yeah. 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 For example, here you can see here that in our FEMA architecture, when we do this, we get the information from the online. First, some uncertainty information and some uncertainty method, for example. Yeah. That the system need to be updated. In our working practice, we do find some uncertainties or not so high quality outputs. So that needs what we need to do is that we update the you know that we use the DeepSeek model, AI model like this. The DeepSeek AI model is updating. Yeah. And our data and method, our data is updating.
Yeah. It's okay. So according to my experience, the uncertainty in the parameters behaves a little bit different than the unmodeled dynamics. So unmodeled dynamic may cause a little bit different. So uncertain parameter maybe moves a little bit the solution. But the unmodeled dynamic may cause and not non-expected movement, and so that was...
Yes, yes. In our practice, we found that the AI processing will give us maybe 90% certainty, yeah, for example. And then we have to, currently we still use manual processing, have to check or to update the AI outputs.
Okay.
Yeah.
Thank you.
We still need AI processing.
Yeah, yeah. Any other question? Okay. Please come.
Hi, Professor. Thank you for this. I wanted to ask about the step of AI processing, because you said afterwards there's still manual processing. And so I wanted to ask if currently that makes the process overall slower, since you need to go through the AI and the manual processing, or whether it's faster than just doing manual processing alone.
You mean the storage?
I mean, so you said there's a lot of data, and then it's processed by DeepSeek first, and then you process it manually afterwards.
Yeah.
Is that faster than just doing it manually to begin with, or is it slower?
Yeah, if we do not clean the data, the work is very slow. So that's why before we collect all the data before we send this data to AI processing, we must do the data cleaning. That data cleaning is a huge work. Mm-hmm. Currently, we also use the AI processing.
Okay.
Yeah.
Thank you.
Okay. So thank you. So it is time for finish this session. But before that, I have a very important duty. Okay.
So, dear guests and our colleagues and our students, so thank you very much that you are here today morning. And after this session will be continues the conference in afternoon in the engineering faculty, and tomorrow morning it's engineering faculty 2, and we are organizing a joint event to this conference. What his name is Submit. So this is the forum of innovation, and if I know well the number, it's in the poster session you will see more than 20 innovations idea about from the University of Debrecen, both of faculties and from our guest universities too. So, and now we would like to say thank you to the presentation, at first to the Nesterov professor, and thank you very much. And after the go, Professor, thank you very much for your interesting education.
Thank you.
And the Dean of the Informatics Faculties opened this conference and this session. So as I am the co-chair, and this functions as I am the co-chair, I would like to close this session in this morning, and afternoon will be continues in the Faculty of Engineering. At first is a lunch. So thank you very much.